Imagine walking into a futuristic kitchen where a robot assistant waits for your command. You say, "Pick up the cup," and within seconds, the robot scans its surroundings, processes your words, and moves into action. It all starts with input. Robots can receive commands in different ways: spoken words, written text, button presses, or even hand gestures. If you're using your voice, a microphone picks up the sound and sends it to a speech recognition system. The robot must break down the sound into individual words, compare them to a database of known commands, and determine what you meant. If you type the command, the process is a little simpler, since the robot doesn't have to interpret speech, only the text itself. Either way, once the robot has received the command, the real work begins. Understanding what the command actually means is the next challenge. The robot's software, often powered by artificial intelligence, analyzes the words in the sentence. If the command is "pick up the cup," the software identifies the action, pick up, and the object cup. But that's not enough. The robot needs context. Where's the cup? What does it look like? How should the robot's arm move? To answer these questions, it relies on its sensors and programming. Robots use cameras and sensors to see and feel the world around them. A camera sends images to the robot's processing system, which then recognizes objects using image analysis software. If a robot has a depth sensor, it can estimate how far away the cup is. If it has touch sensors, it can tell when its fingers have grasped the cup firmly enough to lift it. All this data flows into the robot's brain, where it quickly calculates the best way to complete the task. Once the robot understands the command and has gathered the necessary information, it must move. But movement isn't as simple as just reaching out. The robot's system must send signals to its motors, which control its arms, hands, or wheels. Each joint and motor needs exact instructions: how far to move, how much force to use, and how to adjust if something goes wrong. This is where programming and physics come together. Engineers write algorithms that tell the robot exactly how to move efficiently and safely. As the robot moves, it continuously checks if it's doing the right thing. Feedback loops allow it to make small adjustments in real time. If it reaches for the cup but doesn't grasp it correctly, its sensors detect the problem, and the system recalculates a better grip. This process happens incredibly fast, making it seem like the robot is thinking, even though it is simply following a series of programmed steps. Finally, after completing the action, the robot may need to confirm that it did the job correctly. In environments like robotic surgery or warehouse automation, this feedback is critical. A robot performing surgery must be sure it applied the right amount of pressure, just as a warehouse robot must verify it grabbed the correct package. Some robots respond with a sound or a light signal. Others might wait for further instructions, like where to place the cup. More advanced robots can even learn from their mistakes, improving their ability to follow commands over time through artificial intelligence and machine learning. From the moment you say a command to the moment the robot carries it out, countless tiny steps occur behind the scenes. Sensors gather data, processors analyze information, and motors execute movements with precision. While it may look like magic, it is really the result of careful engineering and programming. As robots continue to evolve, will they one day process commands as effortlessly as humans do? The next time you see a robot perform a task, consider how close we are to a future where machines think and act just like us. Within that simple action lies a world of complex decision-making, proving just how intelligent machines can be.
Got a question about how something really works? Drop it in the comments and we might cover your topic in our next video.